Hello, my name is Chris Murphy, and multi-lens systems, especially the calculations, can seem intimidating at first glance. So in the next few minutes, I'm going to break down the process and how to deal with those. If you have to tackle a multi-lens system and calculate things like image distances for the entire system, then it's going to be a matter of taking it one lens at a time. So first, I recommend that you feel comfortable with doing calculations with a single lens system first if you aren't already. The reason I make that recommendation is that the image that we get from one lens is actually going to be the object for the second lens. And that's going to continue if it's more than two lenses in the system. The first step of this process would be to start with the first lens of the system. Use the object's distance and the focal length of that first lens to calculate the image that would have formed from that first lens. Once you have that image's distance, now we bring in the second lens of the system. And once you determine that distance between the second lens and the image formed by the first lens, now you have the object's distance for the second lens. Again, you're going to use the image from the first lens as the object for that second lens. And then rinse and repeat. Keep going and doing this over and over again for every lens in that system. So if you had a third lens in the system, you would use the image from the second lens as the object for that third lens, and so on and so on. So to determine the overall magnification of the entire system with multiple lenses, you want to find the product of all of the magnifications for each lens in that system. So for example, if you've ever seen a microscope that has times 10 or a times 100 or a times 1000 on each of the lenses that you can alternate, that's telling you that you're multiplying by the magnification of those individual lenses. The overall equation would look like this. The total magnification is equal to magnification of lens 1 times 2 times 3, etc. To see how this can apply, let's take a couple converging lenses. Each of them have a focal length of 10, and we're asked to find where the image is formed and if it's magnified or minimized. So to start out, let's begin with lens 1. And here's your object, and the light would be coming in here from the left. So to do the calculations, we need the focal length of the first lens, the object's distance, and that's going to help us calculate the image distance. So we'll have 1 over 10 plus 1 over 20 plus 1 over the image distance. And in this system, we have two converging lenses. If you had diverging lenses, make sure to use negative values for the focal length, as that's the sign convention. So once we find a common denominator and simplify, we'll have 1 over the image distance is equal to 1 over 20. Therefore, the image distance for our first lens is 20 centimeters. So if that second lens wasn't in the way, our image would form over here, 20 centimeters away from the first lens. We can also calculate the magnification that would have occurred for the first lens by taking the negative of the image distance divided by the object's distance. So since they're both 20, our magnification for lens 1 would just be negative 1. So here you found the image distance from the first lens. And remember that the image from the first lens becomes the object for the second lens. So now we're looking at lens 2. And we're going to use the same equation, just make sure to use the right values. So we have the focal length is again positive 10. And for the object's distance, we just found the image distance for lens 1. We're going to need to use that to find the object distance for lens 2. Since the two lenses are 15 centimeters apart, that means that our image would have formed 5 centimeters behind lens 2. So our object for lens 2 is going to be 5 centimeters behind it. Since the object now is behind the lens and on the opposite side of our light source, we need to make sure to use -5 as the value for the object distance. Now you have everything you need to calculate the image distance. To find a common denominator, simplify, and we'll have 3 over 10 is equal to 1 over the image distance. Reciprocal will get us the image distance of 10 over 3 or 3.3 centimeters. You'll also need to calculate magnification for lens 2 using negative image distance over the object distance. Again, the sign convention is key. Don't forget the negative sign in front. So the image distance is a positive 3.33, but the object is still -5. So to make math a little easier, you can double the top and bottom and have 6.6 over 10 to get the magnification for lens 2 to be 0.66. Now to go back and answer the question, the image distance was calculated to be positive 3.3 centimeters. That tells us that that's going to be a real image that forms behind the second lens 3.3 centimeters away. The total magnification is going to be magnification of lens 1 times magnification of lens 2. That would be negative 1 times 0.66 to get a total magnification of both lenses to be negative 0.66. A negative magnification will tell you that this image is inverted. And to determine if the image is magnified or minimized, you want to look at the magnitude or the absolute value of that magnification. Since 0.66 is less than 1, the image will be minimized compared to the object. So for example, if the object happened to be 10 centimeters tall and the total magnification is 0.66, the image is going to be 6.6 centimeters tall. So again, to tackle these multi-lens systems, just take it one lens at a time, apply the same concepts, and definitely make sure to apply the right sign conventions when you're doing the calculations.